solving strategies, we actually will not discuss any new principles, any new theory, almost nothing new today compared to what you heard already, but we will look at the things from different perspectives. We will go through the stages of the structure determination from data collection to the refinement, and we will discuss possible problems that you might face on the way, their possible causes, and possible solutions or approaches to the solution. It's highly likely that the list of possible problems and list of possible causes is not complete. There can be many problems, many different complications, and I might not have thought of all of them. But nevertheless, I hope that this will be useful as a little reference of what to do, at least as a first impulse, if you face certain type of problems. At the same time, I would very much like if this session could be as interactive as possible, so do not hesitate to interrupt me, ask for, let's say, other problems that you might have faced during the different stages that are not included in the lists, or if you feel that there might be different solutions, different approaches. Let's discuss things also maybe in view of the examples that you already did in the practical sessions. You might already have certain questions or things that are not entirely clear. We do have time to discuss these things in this session today. So the truth is that for a large part of structures that I call simple, well, what is simple you can say only after the solution. At the beginning, when you have a crystal in hand, you cannot say if the structure solution will be simple or not. But for a large part of crystal structures, the structure analysis has really become a click button exercise. If you know how to use the programs, if you know where to click, how to use the options, you will obtain the solution in essentially a couple of minutes from the moment you collected the data. Some diffractometer software is actually already linked with automatic structure solution and refinement software. So, for example, in Chrysalis, there is an option that the program tries to solve automatically the structure on the go. So you're collecting the data, and at the same time, you start seeing the solved structure. And very often, this automatic procedure gives you a cleaned up, ready to publish structure. However, your task as a crystallographer is to recognize if there is a problem. That's already not so trivial. There are cases where it's obvious, but there are cases where it's not so obvious, and it's important to recognize these problems. And then, of course, if there is a problem, then the real job starts, and you need to know how to solve it, correct, and still obtain a good and reliable crystal structure. The best way to solve problems is to avoid them, of course. That means that you should try to do the best job possible at every stage of the structure determination process. This is especially true for the data collection step. It's really worth spending a day or two or even more on finding a good crystal and collecting good data, rather than spending a couple of weeks trying to improve refinement, which is not so nice just because the data collection or the data quality is not perfect. That's the famous GIGO principle, garbage in, garbage out. If you have poor data set, even the best program in the world will not give you excellent refinement, excellent structure. On the other hand, the modern programs are so powerful and the options are so versatile that even if you do not have a perfect data set, and of course I know that sometimes it's simply not possible to collect a perfect data set because there are no perfect crystals. So even if you do not have a perfect data set, with the modern software for data reduction and then structure refinement, you can get good results anyway. Okay. So an overall summary of what type of problems can appear is given in this table. This number 2 in the title is there by mistake. I see that there is just one. That's the first of the 2 tables. So in the data collection, well, the crystal may not be diffracting at all, so you may not get any diffraction signal, or the diffraction is very poor. Then if you process the data, you have problems determining the unit cell. Either you cannot find anything meaningful, or the unit cell doesn't index all the peaks in the diffraction pattern, or the unit cell is unusually large for the composition that you expect, or for the expected complexity of the structure. In the next stage is when you have the unit cell, the next stage is symmetry determination, and then you may have the typical problem is that you have poor R internal, so poor agreement of symmetry related reflections. You may have funny systematic absences that do not really match with any known systematic absences of known space groups. Or you can have an inconclusive determination of the space group. So in the end of the process, there is still a list of space groups that are possible, and you cannot distinguish between them from the data you have. Then the next stage is structure solution, and there, of course, again the first problem is that you may have no meaningful structure. You process the data, you try to do the step from the data to the structure model, which we have done in our exercises using the program Superflip, and the model that Superflip suggests makes no sense at all. There are no clear atomic maxima. So that's one problem. Another problem is that you may have a partial solution. So it sort of is there, but it's clearly not complete. Another problem may be that the symmetry suggested by Superflip is not the symmetry suggested by diffraction data. Or everything that is all right, the structure looks fine. There are atoms at reasonable distances, maybe forming reasonable clusters, or let's say motifs, but still for some reason the structure doesn't make chemical sense. So you see there's a long list of troubles that you may face on the way. Then in the structure refinement stage, of course the most often encountered problem is that the statistics of the refinement are not good, so you have poor R values. What can also happen is that the structure is unstable, so it falls apart. So you have a nice structure model before the refinement, and then you refine, and the structure looks like a random collection of atoms. Very frequent and often difficult problem is strange, inconsistent, or weirdly shaped displacement parameters. And another one, which is always worth checking, is the difference Fourier map, to see if there are some additional features in the difference Fourier map that need to be explained. And then even if you get through all this successfully, you have nice refinement with no funny features in the difference map, nice R values, everything looks good, still that's not the end of the story. You need to interpret the structure, you need to understand the structure, and of course you need to extract the information that you want from the structure. Because nowadays the days are over when people solve structures just for the fun of solving the structure, and getting the structure was the achievement. Now we solve structures because of some reason. We are interested in the material, and for some other reason, it's chemistry, properties, whatever, we need to know the structure. So then when you have the structure, you need to use it for the purpose for which you are solving it. So you need to interpret the structure. And then you can have all sorts of troubles, unreasonable interatomic distances, angles, coordinations, or local charges, or local bond balances, wrong charge balance. Very important thing to consider if you solve a structure and it's not an intermetallics where the charge balance cannot be really calculated, then the structure always needs to be charge balanced. And you may have mismatch with expected composition. So all these problems, and definitely several more that I might have forgotten, you can encounter in the structure determination process. And now we will look at all of them one by one and discuss the problem, what does it mean, the possible cause of the problem, and possible solution. You will see that very often either the problem or the solution will be trivial, or it will actually be no solution at all, like in the first case. So if the crystal is not diffracting or diffraction is very poor, so you see a few spots, but not enough to collect meaningful data. First thing may be that you do not have a crystal at all. It's amorphous material, and then, well, we are crystallographers, and we can't do much with amorphous materials. Of course, you can do diffraction on amorphous materials. You can do things like pair distribution function by collecting the diffraction on amorphous material and then analyzing this pattern to obtain the distribution of interatomic distances. There are many things that you can do with amorphous materials, but certainly not collect single crystal diffraction data. You can have also something that is crystalline but poorly crystalline. Then there is a chance that another crystal will look better. So you can try another crystal. Sometimes you really need to try 5, 10, 20, 30 crystals before you find one that's usable. In such case, if you have a material where there is like sort of diffraction, but it's not really what you want, an option is to collect powder diffraction data and see if you see reasonable signal in the powder diffraction pattern. If you don't, then it means that the material as such is poorly crystalline. If you get some signal to higher angles in the powder, then you might have a chance to find also a single crystal. Well, you can also redo the synthesis. The crystallinity obviously depends very much on the synthesis route, so you can reconsider the synthesis, the crystallization under other conditions, maybe slower crystallization to get better crystals. This crystal damage due to escaping of solvent, this is of course mainly a problem of organic organometallic chemistry. If there is a lot of solvent in the crystal, it may really be damaged when exposed to air. And then it's possible to protect the crystal, for example, with a drop of oil during the measurement, or you can seal it in capillary, or there are other techniques to protect the crystals that are air sensitive or moisture sensitive. So that is another that's with another story. But it's also a frequent case or frequent problem in data collection. If the diffraction pattern looks okay, but the spots are too weak, well, again, this is somewhat trivial. You need stronger source or longer exposure. Longer exposure is always possible, but at a certain point that becomes impractical if you need to collect for days or weeks. Although in not so distant past, it was not unusual at all to collect one data set for a couple of weeks. That happened. I even remember in my PhD I collected a data set on one structure for 5 weeks. So everything is relative. Now 2 days experiment sounds very, very long, but okay, if it's important and if it can give you the answer, it might be worth. Quite useful is cooling the sample to liquid nitrogen temperatures. Cooling the sample decreases the thermal motion of crystals in the atoms in the crystal, and that decreases or increases the intensities at higher diffraction angles and may give you a larger or better better coverage and stronger reflections. Of course, you need to be aware that when you cool the sample, you may get a different crystal structure from what it is at room temperature. There can be a phase transition, so it's not always possible, and you need to check, but quite often this is a good solution to the problem of weak reflections or low resolution of the data. So when you collect the data and it seems that the diffraction is strong enough, you try to determine the unit cell, and then you may fail, or the program fails. Well, actually the program will always give you some suggestion, but the suggestion may be clearly wrong. Well, then one possibility is that you simply have too many individuals in the sample. You have 5, 10 crystals, so you have plenty of spots that do not form a lattice, and then there is no other option than selecting a better crystal. Or if that piece is large, you may try to carefully cut the crystal into small pieces and hope that you limit the number of individuals. You may also have too much diffuse scattering. I spoke about diffuse scattering yesterday in connection with local disorder. So if there is disorder in the crystal, then you get on top of the sharp, strong black spots, you get weaker diffuse streaks or much more complicated diffuse patterns like this one. If you set the threshold for peak finding too low, all these weak features may be extracted as false Bragg peaks, and then it will be extremely difficult to find the unit cell. If you set the threshold higher, the program will pick only these strong reflections that form nice pseudo-cubic lattice. You will find a meaningful unit cell, but then of course you need to consider these weaker features. You need to cope with them somehow, but for the structure or unit cell finding step, you can circumvent the problem by setting the threshold higher. If you have too much diffuse scattering, again, another crystal may give you better result. Different crystals may have a different degree of order, and you may get a nicer result in choosing another crystal. However, sometimes the diffuse scattering is inherent to the material, and there is no way to avoid it. All crystals of the same material will have similar diffuse scattering pattern. And then it means that if you want to describe that material properly, you need to take the diffuse scattering really into account. Another problem is that you find the unit cell looks okay, looks reasonable, but it doesn't index all reflections. There are many reflections. So the unit cell, in normal case, it will never index all reflections. So there will always be a few spots, few peaks in the reciprocal space which will not fall on the nodes of the reciprocal lattice. There is always some noise in the data, so that is normal. But if your unit cell indexes only 60 or 70% of peaks found in the data set, then it's not usual. So one possible cause for this problem is non-merohedric twinning. So overlap of two lattices or presence of two lattices which do not strongly overlap. They may be in almost random orientation. That can be found by inspecting reciprocal space, and in the diffractometer programs you can locate the second individual. So you find the first matrix, then remove the reflections which are indexed by the first unit cell, and you can find another unit cell describing another orientation of the unit cell that describes the second twin individual, and then you can find the twin law. Or if the second domain is weak, you can simply ignore the second domain. Then you convince yourself that you can do it. So this is a case of actually pseudo merohedral twinning, where you see that a single lattice describes only half of the reflections. It goes like this, so it will describe these reflections, but not the second lattice. So then you can define the second orientation, find the twin law, and deal with the data the way we did in the practical session on twinning. Another possibility is that you have a superstructure in the data. So there are strong reflections, like in this pattern. There are very strong reflections. Those are these that are encircled in green circles. But in addition to that, there are a few much weaker reflections in the pattern. And here, if you focus, you'll see that there is a row of weak intensities between each row of strong encircled intensities. A few of these weak intensities seem strong, but this is because of the contrast in the image. They are all much weaker than the neighboring intensities in the main rows. So in this case, you need to transform the unit cell to take these weaker reflections also into account. So you should not ignore them. Then you would probably you would probably solve the structure. It would probably give apparently meaningful result, but you would probably have some apparent disorder, which in fact would be resolved if you included these weak signals in the structure determination. A frequent case, yes? Mm-hmm. Not really, no, because if you ignore these reflections, they will not be in the data at all. So you will do the symmetry averaging only on the strong reflections of the, let's say, average structure, and that will look perfectly okay. And especially if these additional reflections are really weak, you will not notice that this problem during later stages of the structure analysis. You will get a structure which is likely to look okay. You may get a splitting or one or two atoms, or maybe just a little bit elongated or deformed displacement parameters, but not something that would really ring the bell. And all the statistics will probably look okay. So if the superstructure is weak, then it's really important to notice it during the data reduction stage. It's hard to realize later that there was a problem in the data reduction stage. It will, but if it is weak, then the effect will be small. So if you had a reference, if you knew what the thermal parameters should be, then you could say, okay, this one is elongated, but it's difficult to say if this elongation is because of missed superstructure or if it is a real dynamic disorder. So if the atom really is free to vibrate in one direction more than in the other. So in some cases, you will see that the structure doesn't look good, that there are funny, inconsistent displacement parameters. But in other cases, and in many cases, this will not be obvious from the structure solution. And there are many such structures in the crystal structure databases, especially from the old days when the structures were measured by point detectors. Now that it worked. At those days, the data collection worked like this. First, the reciprocal space was randomly searched for reflections. So the diffractometer just made essentially random or systematic but search in reciprocal space in blind. There was a point detector, so it was only either counting signal, or there was just background. And when the point detector found a signal, that was recorded, its position, and then when there were 10, 15, maybe 20 such reflections found, then the unit cell was determined from these 20 reflections. And then, based on that unit cell, the diffractometer collected all the reflections corresponding to this unit cell. So you can imagine that if only a supercell in reciprocal space was found, so weak signals were missed, then the diffractometer, the data collection, didn't include them at all, and you didn't have a chance to realize that you missed some weak signals. So there wasn't the possibility to easily calculate pictures like this, because there were no three-dimensional diffraction data, only intensities of individual reflections. Of course, there were ways to avoid that. You could record precision diffraction images, other things, but it happened often that weak signals were missed, and in the database you then have just an average structure without the ordering that was due to that would be found if these weak additional reflections were considered in the structure determination. So these days it happens less, but especially if you work with structures from databases that were determined prior to, let's say, 1990, you should keep in mind that they may not be as disordered as they appear. There might be a hidden ordering that was missed. I don't want to imply that all the structures prior to 1990 are wrong. Definitely not. There is just increased danger. A quite frequent reason for not indexing all reflections is that the structure is modulated. So then these additional reflections can't be indexed with a reasonably small unit cell, because they lie in positions which are not commensurate with the periodicity of the main lattice. So this is what such a modulated structure may look like. So you see there are spots that lie nicely on a line here, here, and here. And then in between there are spots that form a zigzag like this. So these spots can't be indexed on the same lattice. They are either too close to this reflection or too close to here. These are satellites from an incommensurately modulated structure. The structure is not periodic in 3 dimensions. It still can be described, it still can be refined, but using the approaches of superspace crystallography that I will shortly, briefly outline in tomorrow's lecture. Well, in such case, you should again go to views of reciprocal space like this, or to the 3D view, recognize that there are satellites, and either treat it yourself if you have the knowledge for that, or seek an advice of an expert who can help you treat the modulated structure, or the worst case, but the only remaining acceptable case is treat only the average structure, so ignore the satellites for the structure determination, but then whenever you publish the structure or deposit it or speak about it, emphasize, I know there are additional reflections, I know there is additional order that I, for one or another reason, decided to ignore, but what I present is only an average and not the real structure. This is important it's important to keep track of this fact, otherwise you may provide a structure to someone who believes what you did is the real structure and then may make false conclusions. If you have an unusually large unit cell, then it is quite often a consequence of twinning. This is one such example. It is an example that is very similar, although not the same as one of the examples in the practical session. You see there are rows of relatively sparse rows of reflections, and there are rows of relatively densely spaced reflections. There is also quite a bit of diffuse scattering in the picture, but if you try to index all these reflections on a single lattice, you need this tiny orthorhombic lattice. So tiny lattice in reciprocal space means very large unit cell in direct space, but in fact this is a twin by a reticular pseudomerohedry, and the real unit cell is 4 times larger, and you need 2 unit cells or 2 orientations of the twin domains to describe the pattern. So if you see unusually large unit cells, always suspect twinning. I do not say that there is twinning always, but always make sure that you didn't miss some obvious signs of twinning. Again, what is large unit cell depends very much on your problem. If you have an intermetallic compound with 2 or 3 elements and you get a unit cell of 50 angstroms, it's not likely. It's not impossible. There are intermetallic compounds with immense unit cells, but it's not very likely. So that was the data processing stage, let's say. So now we assume that the data processing stage went well and we didn't find any signs of anything suspicious. I repeat what I said at the beginning. The best way to solve problems is to avoid them. So before you come to the next stage, you should be as sure as possible that there was no problem that you missed in the previous stage. Like that, you save quite a lot of problems in later stages. So we assume we got a nicely looking data set, and we proceed with the structure determination to the symmetry determination stage. So we determine the symmetry or estimate the symmetry from the diffraction data. The first problem is that we are getting poor R-internal, poor matching of match of symmetry related reflections. Let's assume we have an orthorhombic crystal or orthorhombic lattice parameters, and we get high R-int for all lower classes. For orthorhombic, monoclinic, triclinic, everything is say 15, 20, 25%. Well, one cause may be the data are not as good as we might have wished, although it may have looked okay, but it just doesn't give a good result. That can happen. Then again, the solution is just to measure another crystal. You may have weak data, so the data set is essentially okay, but the reflections are so weak that the statistical error on the measurement is so large that the R-int is large. You can make a better measurement. In some cases, you can just live with it. You may still get acceptable refinement and acceptable structure model from weak data. You may have twinning. So if you have twinning, then you need to go to lower class, estimate the twinning from group-subgroup relationships. This is the case of the cesium lithium sulfate. Again, one of the examples you have in the practical examples. This is the list, the table that Jana2006 provides when you do the symmetry determination procedure. The unit cell is hexagonal, and if you look at the list of the internal R values, they go up from the triclinic value of 5.7, which is acceptable. They go up to 11, and for all the trigonal and hexagonal lower classes, it's 14 plus. But there is one setting, an orthorhombic setting in the hexagonal unit cell that gives an R int of 7% or 7.4. So this is a hint that the structure is actually not hexagonal, although the unit cell looks hexagonal, but it is orthorhombic, and it may be twinned by rotations of by 60 degrees to form an apparent pseudo-hexagonal pattern. You may have weird systematic absences. This will not be recognized by looking at numbers in the structure determination wizard, because that gives you only the statistics for normal systematic absences. So you can find this only by inspecting reciprocal space. So we discussed that already. This is the same example. So you may this actually belongs to the data processing stage, but if you overlook it there, and if you struggle with the structure determination later, it's again worth coming back to the distribution of diffraction pattern or in diffraction pattern and look carefully for funny systematic absences. Maybe I can say I didn't prepare the pictures for that, but just a few words. We had an interesting case now with one of your colleagues about that was. Can you remind me of the composition of that material with these funny systematic absences? Yeah, nickel-3 indium antimony. Very simple structure, hexagonal. We looked at the reciprocal space sections and we found very unusual systematic absences. So at first glance, I was convinced this is a sign of twinning, of this sort of twinning. But then when we wrote out the distribution of the systematic absences, or these apparent systematic absences, it was not possible to find a combination of 2 or 3 lattices that would explain these systematic absences. And then actually the real explanation was that in this structure, these unusual systematic absences were caused by a combination of atoms in special positions giving certain special systematic absences and a special projection of the structure along the c-axis, which gave another set of systematic absences that did not belong to the space group. So this is something that contradicts my claim that weird systematic absences are caused by twinning, but this is possible only in the simplest structures where all atoms sit on special positions. And then if you suspect you have such structure, you need to check the international tables for crystallography, volume A, corresponding space group, where you find special systematic absences for atoms in special positions. So there you can see if you might not have certain set of unusual systematic absences present in your structure. But it's a very unusual case. Most of the time, if the systematic absences are in some way funny, they are caused by twinning. If you have funny systematic absences, another possibility may be that you have a commensurately modulated structure. Again, modulated structure, because it is somewhat unusual, it goes out of the box of typical structures, it may be an explanation for a couple of problems or unusual features in the during the determination process. This is an example of such case. This is section through diffraction pattern. You see many strong spots. They actually form a parent tetragonal unit cell like this. But if you want to describe also the weak spots on the same lattice, you need a lattice that is as small as this in reciprocal space. So it's actually a 5 times 5 fold lattice, and then all these weak spots like this one fall in the nodes of the lattice. But this would be a wrong description. Well, wrong for two reasons. One, it is obviously not a good description of this pattern. You see that you are predicting many spots which are actually not found in the diffraction pattern. And the second reason is that this describes a twin diffraction pattern. The correct description of the pattern is this one. So you have a square lattice. It's pseudo tetragonal. It's not quite tetragonal. And then on top of that, there are weak additional reflections which can be described as satellites. So this spot is, or there is a reflection expected at this position and at this position. And then, because this satellite is possible only in monoclinic symmetry, there are actually 4 different possible orientations of the monoclinic structure in the tetragonal lattice, and that gives a 4-fold twinning. So the real description, the correct description of this diffraction pattern is a monoclinic diffraction pattern, modulated structure, and 4-fold twinning. There is probably no software that will tell you this as an answer. You need to look this or see this in the diffraction pattern. You need to contemplate this, maybe gather some experience by going through examples, through your own problems. The first one will be painful. You'll probably spend 2-3 days looking at the pictures and having a feeling you'll never figure this out, but you will, and the next one will be better, and then after a couple of years you will just look at it and see it immediately in half a minute. So just be patient and don't give up. Another set of problems during symmetry determination. You may have an inconclusive determination of the space group. So that is a very general term. So something just doesn't feel okay when you do the structure, the symmetry wizard. This is an example. If you look at this table, which serves as a check for lattice centering, at first glance it looks clear. There are large numbers here, so it should be primitive. But if you look at these numbers more closely, you'll see that, for example, for the C centering, there are only 406 reflections observed out of almost 65,000 reflections that should be absent. So 400 out of 65,000 is a very small number. So it's almost there. The C centering is almost there. But if you look at the A centering, it's not much worse. It's still 1,000 plus out of 65,000. So very few reflections observed or violating the A-centering rules compared to the total number of reflections. So this is weird. 1,158 is far from zero. So there are reflections that violate the rule, but there are just a couple of them. So there must be an explanation for that. In this case, the explanation is, again, twinning. So there are reflections which come only from one or one of 3 twin individuals, and there are other reflections which have contributions for all 3 of them. And then that makes some certain class of reflections weaker, certain class stronger, and that causes these strange statistics of the in the structure in the symmetry determination process. It may be that it is just a special feature of the structure, that there are weak, strong reflections. It may be okay, but if you see something like this, don't just think, okay, maybe I'll let it be. It's really good. It's better to look at the data, look at the reflection pattern, try to understand. And if you understand, then you can say, okay, it's fine, it's all right. But you can also find out that it's not quite all right. Again, you see causes of problems are recurring. The same problem or the same cause may give problems at different stages of the procedure. You can again have superstructure with weak reflections, and these weak reflections contribute very little to the statistics, so you do not see a clear differences, for example, between space group with different systematic absences, because these weak reflections contribute very little to the statistics. So then it comes again to inspecting the reciprocal space visually, seeing the sections, or seeing the reciprocal space viewer in Jana, which shows you the distribution of intensities in reciprocal space, and estimating the diffraction symbol, so the systematic absences, manually and not only based on the statistics. It may happen that the diffraction pattern does not provide sufficient information for the determination of the space group. This is actually not a problem, that's a feature. The diffraction does not give you always a unique answer. The systematic absences together with the lower class are not enough to tell you unambiguously what is the space group. This is an example of a real structure. You get a list of possible space groups, and you see that there are 1, 2, 3, 4, 5, 6 space groups that give no systematic absences at all. So based only on systematic absences and lower class symmetry, they are all 4 over MMM lower class. You cannot say anything about these, about which of these space groups is the right one. That's just the way it is. You may, using statistical tools, you may estimate if your structure has or doesn't have inversion center. Then you would, if it has inversion center, you would, if it doesn't have inversion center, you would exclude the first space group, but you would be still left with 4 other, and you can't say anything about that. So then you have to either try all of them and see in which of them you get this, a nice structure model, or you may use the features of some structure determination programs to estimate the symmetry from the solution. Then you can see if the symmetry that, for example, superflip suggests you, if it is one of these space groups, and if it is, then it's most likely the right space group. So this is not, well, it's a problem for you, but it's not a problem in the sense that something could be wrong with the data or with your data processing. Yes?
Is there any possibility in Jana 2006 to change the statistical distribution?
Yes, you can go to in the menu. There is run intensity statistics. I think the name is intensity statistics, and if you run that, you will get all sorts of statistics, and one of them are these plots or calculations of the mean e square minus 1 value, which is the value typically used to determine, to estimate the inversion center in the structure. Maybe it's a good hint. We can have a look at it in the practical session. I can demonstrate that. It is not directly accessible from the symmetry determination wizard. It may be it might be a good a suggestion for improvement. I think the reason is that these statistics are reliable for light atom structures. For organics, they are quite reliable. For inorganic materials, less so, because these statistics are based on an assumption of equal atoms randomly distributed in the unit cell. And we know that real structures are all but randomly distributed sets of atoms, and inorganic structures are all but equal atoms in the structure. So if you have strongly differing atomic species in the structure and atoms on special positions, this statistics may give you a hint, but the hint may be equally well wrong as right. So finally you have to try both options anyway. So yes, it's there. In practice, what is faster way forward is to try the centrosymmetric space group and run Superflip or SHARIX-T and see what is the symmetry suggested by these programs. And then if you are wrong, you quickly change the space group, run the solution again, and in a few minutes you have the right symmetry anyway. But I will show you in the practicals where to find this option and how to see from the numbers what is the case. With this we come to the next stage, that is problems during structure solution, and it is now almost 1 hour over, so I think we will make a short break and continue after the break. Is supplemented, so there are other spots that do not lie on the average reciprocal lattice, but they can be located away from the lattice nodes by certain vector, and this vector may have either simple coordinates like 1/2, 1/2, so then the additional spot would be in the center of the square of reciprocal lattice, or it can have complicated values like 0.4700, so then it is not quite in any simple fraction of the reciprocal lattice. So if there is a simple fraction, then these values are called commensurate, that means rational proportion, and if there is no simple relationship, then the structure is called incommensurate. I had actually examples of both. This is a commensurately modulated structure because the modulation vectors, so let's say, for example, this spot, this is actually at 1/5 along this direction, 1/5 along the vertical direction, and 3/5, so 3/5 in the horizontal direction. And if there is a commensurate value of the modulation vector, then it's possible to find a supercell that describes all the peaks, the satellites and the main reflections on the same lattice. The lattice is very small in reciprocal space or large in direct space, but it is possible. On the other hand, if you have a really modulated, incommensurately modulated structure, which is this case, then you see that this distance here is a little bit more than 1/2, this distance a little bit less than 1/2. So it's not a simple fraction. It's not 1/2, it's not 1/3. And then this structure would be considered incommensurate. Any other question? Yes.
Sir, how to deal with the sensitive system? Like the problem is, whenever I am taking out the system from the solution, the dissimilarity is decreased. That is, try to make weakness really. So the time I needed to take it out. So this time to deal with that?
Here I should say that I'm not really an expert on this type of materials and in general on data collection of sensitive crystals. So I have just a general idea. Yes, that's one option. So you can seal the crystal in capillary, or you can also put it in a drop of oil. That's a frequently used feature. So there are special loops, a small loop, and then you put a drop of oil in the loop that holds on the loop. Then you fish the crystal with this oil, and the crystal gets covered with a thin layer of oil which protects it from air, and sometimes this is sufficient to protect the crystal. Another option is to cryo, so to freeze it, and then again the crystal is more stable. But the crystallographers dealing on daily basis with these crystals, they have I'm sure they have many more clever ways of handling that. So you should seek advice with experts. But sealing in capillary is a simple and very efficient way of dealing with this problem. The only drawback is that the capillary will give you some more background in the diffraction patterns, because it's also scattering. The glass of the capillary is scattering. But if the crystal diffracts reasonably well, this increased background will not cause serious problems. Any more question? Okay, if this is not the case, then let's continue with the next stage of the structure determination process, and that is the structure solution. Maybe just 2 sentences about the meaning of the word structure solution. When I'm speaking about the process of getting structure model from the diffraction data, I use the general term structure determination. So that includes everything from the data collection to the final interpretation of the data. And there are different stages of the structure determination process: data collection, symmetry determination, and one very important stage is the structure solution. This is a step that brings you from your list of intensities to an approximate starting structure model. In other words, this is the step where the phase problem of crystallography is solved. So we have intensities, we do not know the phases of the diffracted beam, and there are various methods and various programs that allow you to solve this problem using statistical, mathematical approaches, and the result of this procedure is an approximate structure model. That model may be very good, it may be even 100% complete if you are lucky and if your structure is not too complicated. It may be less good, but it is a good starting point. And then, ideally it is a good starting point if everything works. And then the next step in the structure determination process is the structure refinement. And this is an optimization step where you have your approximate structure model coming from the structure solution step, and you optimize the model to give you the best match with the data. So the structure refinement follows structure solution. So now we are in the structure solution step. We have list of intensities. We believe that the list of intensities corresponds to a single domain, so there is no twinning, or at least we hope so. We believe that we estimated correctly the space group, and we want to get a structure model from the data. Now, if everything goes fine, you just get the structure model within a few seconds. This is the step where you open the form structure solution, you in the practical examples we used Superflip. So you click Run Solution, you see a screen popping up for a few seconds, and then it's done. And when you view the structure, you suddenly have a structure model, although you didn't have one before. So that's the solution step. So if everything works fine, you get a solution that is meaningful, and that you can refine further. However, not always everything works fine. And again, you can have a couple of problems. One problem may be that you just do not get any meaningful structure out of this procedure. You get just a randomly scattered set of atoms in the proposed structure. There are, in general, three possible causes. First, again, the data are simply too bad or not sufficiently good, or too low resolution. If you want to get structure model ab initio, you need to have sufficiently good resolution, which is, roughly speaking, about 1.2 angstroms d-min. So the minimal d-spacing covered in your data collection should be 1.2 angstroms or better. In inorganic structures, this value may be a bit relaxed. You can get good solution from data with resolution of 1.5, 1.7 angstroms, but a general recommendation is get data to at least 1.2 angstroms d-min. For some data sets or for some complex structures, even that value may be a bit too high, and you may need to go longer. So if you have poor resolution or low resolution, this may be one reason why the attempts to solve the structure fail. Then again, you need to collect better data, more signal, high resolution. Another possibility is that the structure is simply too complex for the selected method. Too complex may mean too large, too many atoms in the asymmetric unit, or it may have special features like all light atoms, lack of inversion center. These are two features in the structure that make the structure solution difficult. In such case, so you may modify the parameters of the method, but for that you need to know a little bit more about the program that you are using to solve the structure, or you can simply use another method or software. Talking about the software available for a structure solution, I'd say nowadays for small molecule and inorganic materials there are three programs in use. It is Celix-T, which is a successor of Celix-S that was the standard for 2 decades. So most people used Celix-S for solving the structure, and Celix-S was using the direct methods approach. So this is now replaced by Celix-T program, which is using a dual space algorithm. I do not have time to go into details of these things, but just that you at least hear the keywords. So Celix-T is using dual space algorithm, and this is now probably the most popular program for solving structures. The second branch is the family of SIR programs. So SIR, I do not actually know what is the very latest version, but there used to be SIR 2008, 2011, 2014. So there is every now and then a new version of the SIR program that is programmed or developed by the group in Italy, in Bari. This is also a direct methods program, but with many modern features. And the third is the program Superflip, which is using charge flipping algorithm. It also belongs to the family of dual space methods, and that is the one that is distributed with Jana. So it's a separate program, but it is distributed together with Jana. So when you download Jana2006, it is directly available and you can use it. The other two programs are also free to use, but you need to register, get license, and download the programs, and then you can link them with Jana. So if you like Shell-XT or SIR, or if Superflip does not give you a solution, you want to try another software, you can get one of these two, link them with Jana, and try to see if one of these two programs gives you solution. This is the interface for the structure solution, and you see that if you have the programs linked, you have the option to use SIR. You can choose the version that you have. You can use Superflip, which is the default, or you can use Shell-XT. And then, especially for Superflip, there is a range of options that you can change, and that may change the performance of the program. There is a manual for the program which explains the meaning of these options. I will just mention one of these options, and that's use local normalization. This is an option that enhances the intensities or sharpens the resulting density map, and that's an option that's useful for light atom structures. So if you have organic structure and you can't get solution using the default method, using this local normalization can help. Other programs have other options. Possible cause for a problem or for getting non-meaningful solution is also wrong symmetry. If you guess the space group wrongly, try the solution doesn't look good. This applies mostly to SIR, which where you give the symmetry as an input, and SIR tries to solve the structure in that symmetry. Superflip and Shell-XT, they use an algorithm that is much less dependent on symmetry, and it guesses the symmetry during the structure solution process. So you can get a solution, you can get also the symmetry, and you can check that the symmetry suggested by the program is the symmetry that you guessed or estimated from the diffraction. This you have done in the practical session. Actually, in every example, you do the structures and the symmetry determination wizard. You make a guess of symmetry, then you run Superflip and check if the symmetry suggested by Superflip is the one that you guessed. And if it was not, and in some of the examples it was not, you changed the symmetry, you changed the space group, and then ran the solution again. So with Superflip and Shell-XT, you can do this procedure. For SIR, if you are not certain about the symmetry and you are not getting nice solution from SIR, you may try another symmetry and try the solution in another symmetry. Another situation is that you get a solution that somehow looks that it may be fine. There are motifs, there are parts of molecules or parts of coordination polyhedra, but it's not good, it's not complete. There are atoms that are missing or other atoms that are clearly in wrong place. There are again three possibilities. Either the data are of insufficient quality. That doesn't happen so often with X-ray diffraction data, but if you have reflection splitting, poor crystal, that may also happen. In our practice with electron diffraction data, which are in general lower quality, this happens actually relatively often. In that case, either you need to get better data, or if you can't, you can try to improve the model in later stages of the refinement. And this is also what you have done in certain way in the examples that you solved in the practicals. There were small imperfections in the model, maybe wrongly assigned atoms, maybe 1 or 2 atoms missing, and you know that you can complete this in the later stages of the refinement. Another cause may be that the data quality is okay, just the structure solution method is not performing well enough to find all atoms. Maybe some of the atoms are give too weak signal, they are not picked up with the program. Then again, you can try to complete the structure during the refinement process, especially using the difference Fourier map and looking for signal, for missing signal in the difference Fourier map. So the fact that you see only partial solution with missing atoms, this doesn't necessarily mean that you can't get a good structure solution. It just needs some manual intervention. It may need just a manual intervention to improve the model. Again, a possible cause for a structure model that looks strange is twinning. Twinning modifies the intensities. So for the structure solution step, which assumes you have just a single domain, this is such a twinned data set is actually very noisy data set, which has intensities that may be far off from the correct ones. And then if you put noisy data in the method, you get noisy output from the method. This is an example of a result of structure solution from a twinned crystal. This is a potassium uranium silicate, and in this view you can see there are these silicon tetrahedra viewed along one of the mirror planes. So these tetrahedra, if you rotated it, you would see they are okay. This is another tetrahedron, looks okay. This is a uranium 07 cluster, which has 1, 2, 3, this is hidden, 4, 5 oxygen in the equatorial plane, and 1 oxygen above and 1 below. This is a perfectly fine polyhedron for uranium. This here is another silicon 04 tetrahedron, which looks fine, but then there is something really messy here. Just a cluster of oxygens close to each other with nothing in between. These are these flat regions with only closely spaced oxygens. They make no chemical sense. Even if you consider these oxygens may not be oxygen atoms but silicon, even then it's not possible to interpret this part of the structure in a meaningful way. And the reason for this is the twinning. So this was solved in wrong symmetry, in too high symmetry, using data from a twinned crystal. So this is another sign that you may have a problem with twinning. Next batch of problems during structure solution. Symmetry doesn't match the extinction symbol. So this applies to superflip or Shellix T. As I said, these two programs estimate independently the symmetry of the structure, and it may happen that you estimate the symmetry to be P2 over M, and superflip suggests that it's in fact P21 over N. There are in general two possibilities. Either the symmetry determination from the diffraction is wrong and superflip is right, or the other way around. The third possibility is that both are wrong. But you need to then decide yourself which of the two suggestions, if any, is a good one. In practice, you just try, you get the suggestion by superflip, you look at the structure. If it looks okay, it's probably the right guess. But if you want to do it carefully, you should understand why the suggestion of symmetry based on diffraction was wrong. It may be by wrong evaluation of systematic absences. It may be simply because this determination is not unique, as I showed you on these 5 possible space groups in 4 over MMM Laue class. Again, it may be some twinning in the data, so there may be different causes. So if you want to be sure that nothing goes wrong, try to understand why the suggestion from diffraction was not the one that was correct. Another possibility is that superflip is wrong, or shell xt. That also happens. It happens because superflip is sensitive to other features than the symmetry determination from diffraction. So sometimes it just goes wrong. This is one example of such incorrect determination. This is the part that shows you what is the estimated symmetry, and here you see the space group was not found in the database, and the tentative Hermann-Mogen symbol is x 2 over m, where x is a non-standard centering. And here you find the list of centering vectors, and if you look at them and analyze what they mean, they are actually suggesting that your unit cell should be 2 times shorter in both A and B direction. If that is the case, again, you need to think about it, understand why is this the case. It may be that there are strong and weak reflections in the data, and those weak reflections give so little signal that superflip doesn't recognize them, doesn't recognize they are there, and then sees only the structure corresponding to the strong reflections and gives you an average structure corresponding to a larger reciprocal unit cell or smaller direct cell. In that case, if you are convinced that your estimation of the symmetry based on diffraction is right and superflip or shell xt are wrong, you can still insist on using the symmetry that you estimated, and the structure solution may still be correct. Even though the estimation of symmetry is wrong, that doesn't necessarily mean that the solution as such is wrong. So you can still inspect the solution, see if it makes sense, and if it does, you can use it and continue with the refinement process. Another possibility is that the structure looks okay. It looks in some sense meaningful, but it does not make chemical sense. So there are atoms bonded together which should not be bonded together, and this usually has relatively simple explanation, and that is incorrect assignment of atomic types into the peaks in electron density. In the solution, in the structure solution step, the step is actually not from diffraction data to list of atomic positions, but it is from diffraction data to electron density map. And then you get an electron density map which has maxima, and in the next step the maxima are interpreted as atoms. So large maximum in electron density means there is a heavy atom, small maximum means there is a light atom. And it may be difficult to distinguish between atoms that have close atomic numbers, like carbon and nitrogen, or silicon and phosphorus. And sometimes it may be difficult to distinguish even relatively atoms that are relatively far apart, like aluminum and oxygen. So you can get solutions which are actually correct in terms of electron density, but they are incorrect in terms of atomic species assigned to maxima in electron density. That is quite normal, and then it's up to you to inspect the density and, using your chemical knowledge, correct the density. In the practicals, you had this case in the cobalt aluminophosphate, where the solution program suggested, I think, that a couple of oxygens were actually aluminum. So there was aluminum incorrectly assigned to oxygen position, and there was another problem of wrong atomic assignment. In this case, it was again a recurring problem caused by twinning. So the data were twinned, so the structure solution also is not of as good, as high quality as from pure non-twinned data set. But if this is the case, it's usually easy to correct. You see a coordination polyhedron in shape of tetrahedron, so it's clear that the corners of the tetrahedron should be oxygens in normal case. So you just correct the structure model. And yes, so this is sometimes it's not so easy to recognize the chemical problem, even if just by looking at the structure. In that case, you can make use of other tools like the bond valence sums. This is a somewhat artificial example, but this is in this structure. These blue atoms are all silicon atoms. The refinement is beautiful. R value is 2.01, goodness of fit 1.56. You don't find anything suspicious if you look just at the statistics. But then if you do the bond valence sum, you see that for uranium you get something very close to 6 as expected. For silicon 1, this is 3.94, very close to 4 as expected. But for silicon 2, you get 2, which is far from the expected 4. So silicon 2 cannot be silicon, and indeed it's not silicon. This should be magnesium. So you need to use these tools and also chemical knowledge to complete the structure. Another problem for a structure that doesn't make chemical sense is disorder. That means you may have atoms that are in split positions, and of course, if you look at a structure like this, this doesn't make chemical sense because these two oxygens are about 1 angstrom apart, and it's just not possible that two oxygen atoms in such a structure are 1 angstrom apart. What makes sense is assuming each of these oxygens is there with only half probability, and so either one or the other is there in a single unit cell, and then it makes perfect sense again. This is the same case. This is the octahedron disordered in the structure of Sklodowskite. Again, this doesn't make sense. This seems that the central magnesium atom has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 oxygens in the coordination sphere, pairs of oxygens very close. In reality, this is just an octahedron that is disordered between two positions. So disorder is a frequent cause of something that apparently doesn't make chemical sense. With this, we come to the last stage of the refinement. Well, last but one, last stage of determination, and that's the refinement. At the very last stage is the interpretation. And you see that these stages are, especially the interpretation, is not separated completely from the rest. You do some sort of interpretation from the very beginning, trying to make the structure meaningful from the beginning. But let's assume we got to the refinement stage, and we have initial structure model, and we start refining. What happens, or what can happen, is that the figures of merit, or simply the R value, doesn't go down. That can have a number of possible causes. The most simple one to correct is incomplete model. You may have atoms missing in the model. This can be corrected by completing the model, obviously, and the way to find what are the missing atoms, the easiest way is to see, to view difference Fourier map find positive maxima in the difference Fourier map, and these positive maxima show you the places where there should be an additional atom in your structure model. A similar case is incorrect model. So not really just incomplete, but incorrect. There may be one atom too much somewhere, or there may be a wrong atomic type assigned to some of the atomic positions. Again, in the difference Fourier map, you often see this. You may see it as a negative peak if you have a too heavy atom in the position of a light one. If you by mistake assign whatever indium in place of nickel and refine the structure, you will get a large negative peak in the difference Fourier map, showing that there should be less electron density in your structure model than what you have. So you need to either decrease the occupancy of the atom or replace it with lighter atom. You may have incorrect symmetry. It may be surprising to say that you can have incorrect symmetry still at this stage. When we check the symmetry in the symmetry determination process, then again in the structure solution step, then again when viewing the structure model, always we consider, could there be a different symmetry? Still, it can happen that you get to this stage and still have wrong symmetry. This is one of the examples. Again, one from the practicals. You can. It seems that the symmetry is orthorhombic, PMCN. You get a solution that is perfectly meaningful. It looks okay, no problem there. You refine and you get an R value of 23%. You may work on this result, play with partial occupancies, try to force the solution to better result. You get somewhere to 16-17% with all the effort, but not better. Then you go down to P21 over N symmetry, monoclinic subgroup, and you can refine the structure to 3%. So wrong symmetry can happen or can be discovered at quite late stages. Poor R values can also be caused by forgetting to set displacement parameters to anisotropic. That's a trivial mistake, but that just that may happen. So an example is here. This is a compound containing rhodium and indium, and if you refine the structure with isotropic atomic displacement parameters, the R value is 20.85. So that looks disastrous. If you set the atoms to anisotropic, it goes down to 8%. The heavier the atoms, the larger the difference between isotropic and anisotropic refinement. In some cases, you may need to consider anharmonic parameters for heavy atoms, as was the case for the practical example on silver antimony sulfide, where the silver has certain anharmonic shape, and shifting for the silver from harmonic description to anharmonic actually decreases the R value to almost 1/3 of the original value, so dramatically. And again, another possibility is that you have twinning, and then you should check that a better solution can be obtained in a subgroup with twinning. Another problem that occasionally happens is that the structure falls apart. So the structure model that you have after the solution is okay, but then you do refinement, and the atoms move around in the unit cell, and the result doesn't make any sense. One possible cause is that your structure model is just seriously flawed. It's not. It doesn't match your data at all. This hardly happens if you do a normal procedure, but it can happen if you try to combine data with a structure model obtained from some other source. Typical case, you have data on a material of which structure is known, and you want to import the structure model from the database and verify if it matches your data. So you import the data, you import the structure model should be okay because it's from the database. You try to refine and you get a terrible result. And you start thinking, oh, what happened? I collected wrong data. In these cases, the explanation is usually very simple. Either your data and the structure model are in different cell setting, so there is a cell transformation between the two, or there is a mistake in the list of chemical elements. So the order of chemical elements in the model that you import is different from the order of chemical elements as you have it in Jana. And because Jana does not determine the chemical elements from the names of the atoms, but from the numbers, so if you scramble the order of chemical elements, you scramble the atomic types, and then you can have indium instead of oxygen, and oxygen instead of iron, and everything goes wrong. So if you are combining data from different sources, or data and model, or if you are doing any non-standard operation on your files, you need to check that everything is consistent. I know this is almost trivial to say, but I know from my own experience that this happens more often than I would have wished myself. Another possibility is that the structure is unstable because of strong correlations between parameters. You can see this in refinement listing of so view of refine. This is how it is called in Jana2006. At the end of the information, you have a list of strong correlations, and you may find a picture like this. So this is a refinement of a very simple structure, quartz structure. In the first picture, you see the refinement in the space group P3121, and it's a nice refinement. And the second example is the refinement in the space group P31. So a non-central, well, not non-central symmetric, both space groups are non-central symmetric, but a subgroup of the first one. And the refinement is better. The R value goes down from 2.74 to 2.56. So you may say, okay, improvement of an R value, so that's a good way to go. But you have 29 parameters instead of 17, so a large increase of parameters. And then if you go to refinement listing, you see there is 1.000 correlation between the Z coordinates of silicon atom and oxygen atom, another silicon and oxygen, and also the Z coordinates of two oxygen atoms. So what happened is that by going to too low space group, we made two atoms independent which are actually related by symmetry. And then a change of the position of these two atoms has exactly the same effect on the diffracted intensities. And therefore, the two parameters can't be determined independently. And it may happen that one atom goes up, the other goes down. On average, they are still the same. And you get something that is actually much worse in terms of accuracy of the structure than what you obtain in the higher symmetry. So having too high symmetry is not good, but having too low symmetry is also not good. And that you have too low symmetry, you may recognize from these large correlation. A large family of problems is problems with displacement parameters. You can have weird, in general sense, inconsistent, strangely shaped displacement parameters. This is always unpleasant because displacement parameters are the litter bin of structure determination. So the errors in the data, mistakes in the model, they, not all, but many of them go and can be hidden in the displacement parameters. So you can get refinement that looks okay, and if you view the structure with atoms as spheres without displacement parameters, it may look okay, but then if you view the displacement parameters, you see that things are actually not good. One cause may be wrong absorption correction. That's actually one important cause for poor displacement parameters, and for today afternoon we prepared for you one example that shows how this can be the case. But you may simply have insufficiently accurate data or insufficient amount of data, so low resolution data, not enough reflections, and then there is simply not enough information in the data to refine independently the displacement parameters of all atoms. So then you have two solutions. Either you use only isotropic displacement parameters, so you have only one parameter per atom instead of 6, or you may restrict the parameters of similar atoms to be the same. So that's even further step. You say, for example, all oxygen atoms have the same displacement parameters. This may be an approximation, but it's better than letting the displacement parameters go wrong. And this is an example of such case. This is electron diffraction data. These things happen less frequently for X-ray diffraction data, but as an illustration I used a structure determined from electron diffraction data, and the left picture shows you the case when all displacement parameters were refined independently as anisotropic, and you see that this goes terribly wrong. All these boxes mean that the displacement parameters are non-positive definite, so negative, physically meaningless displacement parameters, and there are really weird things happening all over the structure. So what you can do is you can go to isotropic displacement parameters, and what you get is something that looks less terrible. Most of the atoms have now positive displacement parameters, but not all of them. But you can still see big inconsistencies, like here these three have very large displacement parameters compared to these two, although they are in the same molecule. Here the difference is also very big. So this is still not really satisfactory. So what we can do is we can restrict the carbon displacement parameters to be the same, and the oxygen displacement parameters to be also all the same. And if you do that, you obtain a model that may not capture all the details of different vibrational freedoms of different parts of the molecule, but at least it looks reasonable and more acceptable than the previous two. So this falls in the general class of problems that you should not over interpret the data or ask from the data more information that it can provide you. If some information is not in the data, like here the information on anisotropic movement of each atom, then you simply cannot extract it from the data. You can also use molecules and TLS tensors instead of individual ADPs. This is again an example that you can take from that you can do in the practical. It's the inorganic molecular crystal, and the whole molecule can be described as rigid body, and then you can describe a collective motion of that molecule with TLS tensors rather than individual displacement parameters of each atom. On this picture you see that these TLS tensors can also go wrong sometimes. So here most of the molecule is okay, but these terminal hydrogen here, they get negative displacement parameters. So in that case you still need to do some restrictions on the TLS tensors to prevent these physically meaningless results. Large displacement parameters, especially large displacement in one direction, are a fingerprint of disorder. So then you need to describe the disorder by splitting the atomic positions or introducing two or sometimes even more molecular position. And I'm using again the same example that I used already several times. This is the magnesium 06 octahedron when refined with only one oxygen position, and you see that the oxygen has a very elongated displacement parameter, and this is really a clear sign that in reality there are two positions of oxygen, one here, and if you place only one atom, it just desperately tries to describe the electron density of both atoms at the same time, and it refines to such a long anisotropic shape of the displacement parameter, and then you may split the atom and you obtain something like this. In this case, it is usually not possible to refine anisotropic displacement parameters of both of these atoms. They are too close to each other, and their ADP parameters would correlate, so it is advisable to keep these atoms as with isotropic displacement parameters. Another cause for wrong displacement parameters is incorrectly assigned atom type or atom with wrong occupancy. Then you may consider choosing a lighter atom if ADP is too large, or heavier atom if the ADP is too small compared to its neighborhood. Another option is considering partially occupied atoms if that is crystal chemically reasonable. One example is the cobalt aluminophosphate. This is what you obtain if you refine the structure as it comes from the structure solution step, and most of the structure looks okay, but one of the cobalt atoms gets this huge displacement parameter. That means that the refinement tries to spread the electron density of that atom into a large region, and that means that the predicted electron density of the cobalt on this side is way too high for the expected electron density. And the solution here is to refine partial occupancy of the cobalt atom, and it refines to a rather low number. I don't remember it by heart, but it's something like 10 or 20%, something like that. So low occupancy, and in this case it is chemically very reasonable. You have an atom in the center of a polyhedron which may and may not be there. If you remove it, the rest of the structure still remains chemically reasonable. In other cases, you cannot simply do it. We had a look at a structure yesterday and with one of your colleagues, and there seems to be a chlorine atom which has more than 100% occupancy. Well, that is certainly not possible. We still do not know what is the reason for that. But there are things that may improve the refinement but can't be done because they are meaningless from the point of view of chemistry. To summarize, it is always good to try to understand signs of problems when they come. Nowadays, when the whole structure solution process or structure determination process may take a couple of minutes, it may be less of a concern. So you can just first think, okay, I do the click procedure and see what comes out, and if what comes out is okay, then I'm happy and I don't lose my time checking for the details. Most of the time, or if that works, most of the time it's okay, but you can still do a mistake with this. You may miss small hints of small features in the structure that you do not recognize in the final solution, like weak superstructure reflections or modulation. So you are happy with the result, but the result may still be wrong, or at least not as right as it could be if you did everything right. But then if you if you miss some of the problems on the way, it is usually more difficult to discover it at later stages than in the earlier stages, because at later stages, example, you get high R value, it can have a long list of possible causes. But at the early stages, if you check carefully for the unit cell, the list of causes for problems there is shorter. So it's better to remove some of the possible problems early in the way. So do not overlook or try to mimic or remove the warning signs. An important point, good R value is not a proof of a correct structure. You can get a nice R value with a wrong structure. It's usually not completely wrong, but, well, partially wrong is still wrong. So that's very important. You should never use an argument, I got a good R value, so where's the problem? That's not an argument. R value is a sign that your structure may not be or may be correct, but not a proof. If you want to avoid problems in the publication stage from nasty referees, be your own referee. You know? Submit papers and do crystal structures so that if you got it from someone else, you would not be critical to their work. This is sometimes harder to do than to say, but it is really important. And final word, I haven't spoken much about structure validation. Structure validation is not included in Jana 2006, or at least not to as much detail as it is in the program Platon, which is the golden standard for structure validation for standard structures. And if you submit a structure to IUCR journals, so International Union of Crystallography, and also many other journals, you'll be required to submit a CheckSIF file, which is an output of a check of the structure with the program Platon, and there is a lot of checks being done on your structure. It's a very annoying procedure because many of these checks point to problems which are actually not real problems in your structure. And you're still asked to correct them, to add a lot of small details about the structure. How did you measure? What was the color of the crystal? Nobody cares what's the color of my crystal. Yeah, it's opaque, but still you have to type it there. Many annoying things, but among these things there might be signs of real problems. So the structure validation is your friend, not enemy, although it seems so. So be careful and try to understand the alerts that you have and cope with them again in fair manner and not just in a way to somehow get rid of them without really understanding what they mean. With this, I conclude the lectures on structure determination of structures using Jana 2006, with the exception of two special cases which we will cover tomorrow, and that is structure determination or description of modulated structures using the superspace formalism, and a structure solution from electron diffraction data, which can be also done in Jana in a way very similar to dealing or handling X-ray diffraction data, but it is experimentally, obviously, very different approach. Thank you for your attention. Yes? Okay.